Hello everyone. In this video, let us learn how to use FEKO 2021 Student Edition license to design a dipole antenna. We chose to design a dipole antenna since it is one of the simplest antenna designs to begin with. Note that this video is merely to aid learning and not for any commercial purposes. Double-click on the FEKO 2021 icon on your desktop. A window of Altair FEKO 2021 opens. Now, double-click on CAD FEKO and wait for the Altair FEKO CAD environment to open. Once you have the environment open, click on New. The workspace will be available for you. Now, the first step in design of any antenna is to define some variables which will help us design our construction. Okay, so in order to do that, first you need to know what are the variables you would like to set or define. The most important and the primary variable will be the frequency of operation. Secondly, you will have lambda, that's the wavelength of operation. The third parameter will be the thickness of the dipole antenna. So we define the thickness in terms of diameter, and once you have these parameters set, we can go about the construction. So let's begin with setting up the variables. So click on the variable under definitions. The create variable window will be open. As I said, the first parameter will be frequency. So let me call it as F. You can name whatever you like. And the frequency of operation that I would like to choose is, say, 2.4 gigahertz. So 2400 megahertz. Okay, so check if the value is right and say create. Okay, once you have the frequency defined, you can now define the second variable, that is the wavelength. So maybe you can call it as lambda, or we call it as wavelength. I'll give it as wavelength, and the expression for a wavelength will be c by f. So c is speed of light. You will see that FEKO has defined a few parameters here on the left hand side under variables. So C naught, the speed of light, is already defined. So let's define C naught upon F. This is the expression. Evaluate. Check if the value is right. Say create. Okay. The next parameter I want to define is the thickness. I will define it in terms of radius, okay, and the diameter of the wire I want to choose is half an inch, so that is 0.635, okay. So half of 0.635 will be my radius. You can define the diameter first if you want, and then the radius. Both are fine, but you will have an additional variable to define. So what I will do is I will define the radius. Okay, so radius is 0.00635. Please note that the values entered are in meters. So 0.00635 meters divided by 2 is my radius. I'll say evaluate and create. So now I have the radius as well. Okay, fine. Once I have defined all these parameters, now I'm required to construct the dipole antenna. So in order to construct, let's go to the construct tab, click on line. So you will have a create line window opening. Now here the dipole lies along the z-axis, okay, with it is center fed with half of the length of the dipole on the upper half of the interface, that is the xy plane, and half of it below. Okay, so now half of a half wavelength dipole is lambda by 4, and so I will say, but along the x and y, the parameters are 0, so u is 0, v is 0, and the length on the upper half will be minus wavelength. So I have wavelength divided by 4. So quarter wavelength on the top of the interface, that is the xy plane, and quarter wavelength on the lower side. So again, and u and v are 0, n will be wavelength by 4. So once you have this, you can say create. Fine. You see that the line is created here. If you want to view it, you can go to view, say zoom to extents, and you will see the yellow line along the z-axis. That's your dipole. Now currently the dipole doesn't have a diameter. Okay, so now I need to give it a diameter or a thickness. So I will say just go under details, go to wire, um, right click on the wire, say go to properties, under properties, say wire radius, click on local wire radius, and you have already defined the radius, so just use the parameter. Medium will be perfect electric conductor where losses are said to be ideally 0. So this is fine. Say OK. Now you have defined the diameter of the wire, and you can see the small circular icon here. So that shows that the diameter is defined. Now it's time for us to define the port. As I have already mentioned, in a dipole antenna, we feed in the center. Okay, so the port will be should be fed in the center. So go to wire, right click, say create port, wire port, and now choose middle. Okay, fine. So you have middle, you say create. So you can see here under your construction, apart from the variables, okay, that you have defined, you also have the geometry. Under model you have geometry wherein you have the line and you have the port defined. So you have all of this done now. So it's now time for us to choose the source to our antenna. So we'll go to source or load tab, click on frequency. Okay, since I would like to sweep the operation along a range of frequencies, I will choose continuous interpolated range. The frequency of interest is frequency of operation is 2.5 gigahertz. So I will choose a range from 1 gigahertz, 1 e raised to 9 to, I will say, 3 raised to 9, that is 3 gigahertz. So yes, 3 into 10 raised to 9, say OK. Fine. Once you have set the frequency, now it's time for us to give the voltage source. So let's click on voltage source. The window to add your voltage source appears. At port 1, the magnitude, let it be 1. Okay, you can choose the reference impedance. It may be 50 ohms, it may be 75 ohms. Whatever is your design criteria, specification, choose that. So I'll leave it at 50 ohms. I'll say create. So I'll see on the left hand side, you see that there are the frequency is defined, the electric source is also defined. Now that we have both the sources defined, so it's time for us to look at some post-processing. So in post-processing, we are setting parameters for near field or far field measurements. Okay, so let's go to request now. Under request, click on far fields because I want to define the sphere for far field radiation. It can be in two ways, either in spherical or Cartesian. So if you choose spherical, you will have to give the limits of theta and phi, and if you choose Cartesian, you will have to give the limits of x and y. I'll choose spherical. So we know that theta varies from 0 to 180, but I would like the variation of theta to be from 0 to 180 and on the other side all as well 0 to minus 180. So I'll say in all it's 0 to 360. FEKO is intelligent enough to pick it up. So 0 to 360 for phi as well. Fine. So the incremental length in angle while it plots, I want it to be 5 degrees. Okay. Now you see the 3D sphere here. If you see, look at the horizontal cut, you will see this is how the sphere will be cut. This is the vertical cut. The vertical cut can be either along XZ or YZ. So you have the vertical cut along XZ, vertical cut along the YZ. It is not slanted. You can see it that way. You can change the view and yeah, if you see this. Okay. And finally, you have the 3D pattern. Fine. So this was just for our understanding. Now say create. So your sphere is also ready. Okay. Now, once we are done with this, it's time for us to set our meshing. So let's go into meshing. Say create mesh. Okay. Let the mesh size be standard and we will have to give the global wire radius under options. So let's give this to be equal to radius divided by 2 or 3. It only defines the resolution of meshing. So I'll choose radius divided by 3. I'll say mesh. So I can see the meshing here along the dipole antenna. Fine. So once we have this, I will now want to um, it's now we are ready for simulation, but before we go for simulation, we have to do a small test. So we will first validate our design to check if there are any mm, errors or warnings. So go to solve or run, okay, and we say CEM validate. When the validation is now completed and you see you will have to check for any warnings or errors and you see that everything is green. Okay, so we are good to go with our simulation. Yeah. So now in order to begin our simulation, so we now have to go to another environment. So in the same solve or run tab, you will find post FEKO, which will do the post processing for us. So you have to click on post FEKO. Excuse me, we have got to simulate it first. So let us go to FEKO solver and click on FEKO solver. You see that we haven't saved it. So let's save this experiment. So it is 2400 megahertz. It's a dipole antenna. Okay, so I'll save this. After you have saved, you see that it automatically starts simulating. And once the simulation is complete, you will see the progress bar. Both the progress bars will be green. You can also check for any notices, warnings, or errors. So it will take a few minutes for the simulation to complete. Yeah, so now we see that the simulation is completed. Let's check the notices, warnings and errors. So no what warnings or errors for us. So click on OK. It's now time for us to do some post processing, for which we will use post FEKO. So let's go into post FEKO environment. It will open the post FEKO environment for us. So here we are. So you have to know as to what are the measurements you would like to see. So the most common measurement that each one of us would like to see is the reflection coefficient versus frequency plot, or the return loss plot, what we call normally. So let us now go for it. Okay, so I will choose Cartesian here, since I know that the return loss plot is a Cartesian plot. So click on Cartesian and you have a window like this. You can now, in order to plot the reflection coefficient, I have to um, look at the voltage source. So it return loss means the amount of reflections at the feed point, okay, with respect to the amount of incident energy. So let's take the voltage source, drag it and pull it here. Okay, so I have a good plot that is seen here. I would like to have a few cursors. So let me take the cursor. So let me fix the cursors. So the cursor here at the dip, you see that at it is resonating at 2.255 gigahertz. Okay, and the value of reflection coefficient is 0.167. Instead of reflection coefficient, if you would like to see the return loss, then on the right hand side under quantities, if you have here the reflection coefficient is chosen, just click on dB, and so now you have the return loss plot. So you see that it is minus 16 at 2.5 gigahertz. Now note that there is a shift in frequency. That means the length that we have considered is zero point 0.5 of lambda, which is which probably should have been 0.48 or 0.47 lambda. Well, that can be tuned. So let us go ahead with the post processing. Fine. So I can check whether the return loss is satisfactory. I can also calculate the bandwidth from this plot. To calculate the bandwidth, I will take the 10 dB, the frequency points where I have less than minus 10 dB return loss. So place the cursors accordingly where you have. It should be less than 10 dB. So okay, I'll go by this. It's 9 point minus 9.89. So here you see the bandwidth will be 2.368 minus 2.161 gigahertz. So that's the bandwidth that you have achieved. Well, uh, the next parameter that I would like to see is VSWR. So I will go into VSWR. Okay, at the same frequencies that I had marked the bandwidth, you can see that the VSWR is okay. I've changed the axis here, so you will see that the VSWR points are less than 2 at both the frequencies, and of course in the center at the resonant frequency also it will be less. Fine. So this is about how to measure your VSWR. Of course, you can always improvise on your return loss and the VSWR by going back to the design, but this is just to show as to how to design a dipole antenna and check on the post processing using FEKO. So hence I'm not going into tuning or altering the results. Okay, so now let us look at the impedance matching. Okay, so there will be, it will be nice to see this Smith chart, okay, of the plot. So okay, now have the Smith chart here. To see this Smith chart, now drag the voltage source onto the Smith chart, and you see here the Smith chart. You can also put some markers. Okay, so you have this marker here, and you can check the impedance at each of these points. Okay, so you see here, this is the normalized impedance and this is the denormalized impedance that you see. Okay, and the frequency also varies. So you see that as you move the marker, the frequency varies and the impedance varies. So this can be a good tool to analyze your results. Okay, now finally coming to radiation pattern. Now we will now want to plot the radiation pattern. So go to home, under home choose polar. So I want the polar plot 2D radiation pattern. Okay, drag the far field onto this. So you see here half of the 2D radiation pattern. To view the complete pattern on both sides, click on theta wrapped and you will see here the figure of 8, which is the E-plane pattern of the dipole. Okay, likewise, if you would like to see the H-plane pattern, you will have to click on 5 and you will see here the H-plane pattern. Okay, let's go back to theta wrapped. Fine. And now it's time for us to view the 3D radiation pattern of the dipole. So go to results, okay, and click on 3D view here, standard configuration. You arrive at this. Go to results on the left hand side, okay, and click on far field and you will see the 3D radiation pattern. Also, once you have the 3D radiation pattern, you can measure the gain of the antenna. The gain of the antenna is given on the left hand side top corner. You will see that the red is the portion of maximum radiation and blue is the least, that's the null point. So you will see the gain to be 1.575, and that is for you as to how you can use FEKO to design a simple antenna like dipole. You can use the same technique to design any antenna that you wish. Thank you very much.